Un placer hoy presentaros a nuestro invitado ponente, a Yuri Korchev. Yuri es un biofísico que en estos momentos está en el Imperial College en Londres y es, yo diría que dentro de la tecnología óptica para visualización de altísima resolución, es uno de los investigadores pioneros, posiblemente el más avanzado en este campo. Aquí tenéis una oportunidad hoy, sobre todo los estudiantes que estáis haciendo vuestra tesis, de poder, una vez presentada la tecnología que Yuri nos va a presentar, el poder pensar en las posibles aplicaciones para vuestros proyectos, porque si bien el equipo de Yuri está desarrollando toda esta magnífica tecnología, cierto es que están buscando las aplicaciones biológicas para la misma. Y de ahí la sinergia que ha tenido, por ejemplo, con nuestro grupo, a través de Ainara, que se encuentra desarrollando allí parte de su tesis doctoral, donde una de estas tecnologías, y en concreto la del Scanning Conductancia microscopio, es la que está utilizando Ainara para poder localizar en neuronas sensoriales poblaciones de receptores que responden a distintos estímulos, en su caso al ingrediente activo de la cafeína o del chile. Por lo tanto, vais a ver unas tecnologías de altísima resolución muy exquisitamente definidas y que yo creo que si tenéis alguna aplicación para vuestra tesis doctoral, lo que tenéis que hacer, sin dudar un momento, es hablar con Yuri y establecer una colaboración con él para poderlo aplicar. Él estará encantadísimo de tener todas estas aplicaciones y de ayudar en el uso de esta tecnología. Y ahora ya, si me permitís, voy a cambiar al inglés. Yuri, I was just telling them that your lab is one of the pioneers just developing all these magnificent technologies in the optical resolution, and if they that are doing now their thesis, they see an application of your technology for their questions, that they should contact your group just to make some collaboration, because you are looking for all these applications, biological applications of this wonderful technology. And as I said, that you are a professor in the Imperial College, specialized he is originally from Ukraine, right? He studied in St. Petersburg, and then he moved to do the postdoc to London, where he stayed, got a permanent position, and now he is a professor there developing all these wonderful techniques. Now he is back collaborating with Russian scientists, and he just told me that he got in 2 weeks a grant for 5 months and £200,000. So I like him very much, you know, because 5 months, £200,000 is like 300,000 euros, and just it took 1 week just to write the grant, and 1 week just to evaluate and give the money. So fantastic. I never seen something so speed, you know. But here is, I can tell you that here I got a grant last year. It's supposed to start in January 1st of this year, and I still did not get money. So that is the other side of the coin, right? So thank you very much for coming to Alicante. It's a great pleasure to host you here in our institute, and we are just looking forward to your presentation. Thank you.
Thank you very much. Thank you very much, Antonio, for inviting me. It's a beautiful town. I enjoy very much. We spent time yesterday, and I said that we have to move the laboratory here at least for 5 months, because when we see sun, we're so happy we all ran out and stayed. It will be 2 hours and then finish. That's you have to wait weeks till you get another one. But anyway, this is a fantastic place. I've never seen so many palm trees. We went to the botanic garden. My goodness, they brought them from Australia, from America. They all grow here. It's a wonderful place. It's fantastic. So I will talk. This is a very strange technology to start with, because I mean, why we need another microscopy? There are so many wonderful techniques. You know, and this. I'm sorry for this name. It was not produced. This has been invented by one guy who was from America, called Huntsman. He did mainly atomic force microscopy, and he had decided just to try patch clamp impact to image the current through sample, like people use patch clamp pipette to study the ion channels. But then it was quickly realized, if you not make a gigaseal, you can't record this channel. You cannot even detect the current if you're from a distance. And the technique was forgotten practically. There was no use for that. But what we realized that micropipette is a perfect proximity sensor. Who is familiar with electrophysiology, they know if you have this pipette and come close to the cell, suddenly the current drops, simply it's obstructed. And just simply to understand, it's just a pipette filled with your gross media or loss solution and there. And you put a weak voltage and you have a current. But anything flowing into the pipette will be obstructed when you come close. So it's a sensor which can feel the surface from a distance. And that gives a very big advantage for imaging. I'll explain why we need this imaging technique. So if you look at this scale, how, let's say, resolution versus how invasive the technique, you will see quite a nasty trend. So very good here, but as soon as we want higher resolution, we have to kill everything dead. So could we fill this gap somehow and record something with a high resolution but on a live specimen? And actually it's a big problem. Of course optics now penetrate that because you have a sensor now with super resolution, you can record a particular fluorophore with much higher resolution. But it's again restricted, it's very specific. So we need some other technique which can help us. And this is where we need this scanning line conductance microscopy to help, because we actually maybe can get this resolution. How it works, I'll just explain. If you imagine it's just unbelievably simple technique, because imagine you have this sharp pipette which you can easily produce, make a capillary pool, heat it up. And you can end up with very sharp tip, sometimes 10 nanometer. And because it's a proximity sensor, you don't need to touch, you can move. And if you put like a feedback control to keep this distance, so when you come close, the current shut down, but you just move it out and you move around, so you will get a picture of the cell. But this cell's intact, you don't need anything to do to that. And they all in a buffer solution, so you can do that. And this is the principle how it works. Simply you approach, the current versus distance will drop, and then just keeping the particular position of distance, you can control precisely the distance. And that is fantastic. You can fly over the sample practically without touching it and grab a picture like scanning a microscope, like the electron microscope. But it's alive in a dish, like it's supposed to be. That opens quite the possibilities. So the technique is simple. It's very much related, if anybody heard of that, atomic force microscopy. You just put some piezo manipulators so this pipette can move under the computer control. And actually everything will be generated on the computer. And that will be a topography, like you have a map of mountains somewhere. And this is how the microscope looks like. So it's like a pipette, on holder, some dish with a sample, you just move in and you scan. It's optical microscope, maybe to choose the victim, or maybe to combine with optical measurement. Then everything will be generated. When we first done it, we just attached pipette to that and tried to move. We were completely impressed. The system was primitive. We just put a few pieces of touch pipette, just put on the table and run the computer. And suddenly we started to get this 3D map. It's on the other side. You have to know how to read it. So the grayscale, the white is higher, and let's say the darkest point will be your color scale. So it's a 3D picture. And you can plot it in 3D. So we started to look at what potentially the resolution could be, and we just looked like a filter. You can buy this nuclear or filter they use for filtration. And this is 50 nanometer core. And you can see just using sharp pipette, you can easily see 50 nanometer holes. And even some smaller structures. So the resolution is pretty good. And if you pull a sharper pipette and put a calibration sample like S-layer protein, which you can find in the bacterial cell. And this is like a very nice sample, it's a two-dimensional crystals. So you can see just with sharp pipette, you can see proteins, and actually you can even see protein structure. Because this is 30 nanometer pitch between proteins, and you can see them nicely. Just using this nano pipette attached to the few pieces, suddenly you have a resolution of proteins, so you can see that. But the beauty, you can see it not only on this sample, but you can get the same resolution on the cell, on blind cell. For example, if you look at the sperm, we just look at a particular area, and this is 3 minutes apart, the images, you see these protein complexes. The resolution, this is about 200 nanometer, and this will be 100 to 20, 30 nanometer complexes, and you see how the modifying time, some remain, some disappear. But where they're coming from? They're coming from a sperm cell. And again, this is a picture which you got through the pipette. What we did, we just color coded, so you see sperm attached. And here we can plot it like electron microscopy, simply put a slope. So what you see here is what the angle to the sample. So sometimes it gives you much easier reading because people like that because they're used to electron microscopy. So you always can present like that. And so if you go, for example, after Ackerson reaction on sperm, then you see this release happen. This equatorial region where the after Ackerson reaction, this adhering protein immediately exposed, and this is the region which is responsible for adhering to the end. And you see these complexes with protein complexes in imaging, and this is a free structure of that. It's all integral protein. And that is kind of matching electron microscopy, what you will see. But of course, you deposit metal and you alter that. But this is, if you zoom on it and started to look at these protein complexes, you see some of them remain positioned very nicely, some undergo some changes, and you suddenly get it's the highest resolution ever obtained on live cells. So if you think like that, it's the highest resolution available to man. So you can see that a single protein just run and join the complex, or like this place, for example, this one just broke into the fine liner. So you can actually follow quite a dramatic resolution on the cells. But what is important is just this pipette, nothing else, and you're just moving around. But the problem with biological sample imaging, because they're so elaborate, you imagine if you go to neurons, it's like a spider or octopus in space, everything. And most of the scanning probe microscopy technique, like atomic force, you have to drag a sharp point across, and you will just break everything, because you can't do that. Because here, you're not touching, but our sensor only at the tip. How we can avoid this collision? So we introduced so-called hopping procedure. So instead of just dragging the probe like a blind, just hit the object and then realize that you smash something, you always just jump up and land. So in this case, you can avoid this situation where something on the top. And this is too classical situation. If you look at the neuron imaging this continuous mode, because where the body expands, you cannot sense, you push it and destroy it. But we got this image before with hopping, so everything perfectly picked up before it was destroyed in this mode. And with that, we can get a very high resolution and very high depth of focus, which we will never get with optical microscopy, which is for fun trying to this Drosophila eye. This is electron microscopy, but this is how we see this picture scanned with our microscope. And this is a huge structure because even 40 micron or 50 micron up, and you can pick up this even very tiny spike on the surface. But when you go to the higher scope, what we also introduced is something, because it's slow, you have to hop. So we just hijack something like that from JPEG compression. So you can imagine you can see it's much smaller file, but you don't lose in resolution, because what is happening, for example, not much the image of the empty glass, and we want to focus on the cell. So what we did, we just preview some small area and then decide what the resolution and what the height of the pop. And by that, we can increase speed 100 times. So we can do very rapidly and actually follow that. So you will see that number of density of points will be very different. It's almost a JPEG file. And you can grab a picture with very high resolution without missing the point. So it's very effective, it's automatic, you don't need to do anything. So when we look at, for example, neuronal structures, very complex, and you can just image this very, very complex network and go like this axon down to the bottom. It's kind of suspended, it's 50 nanometer wide, but suspended, like a micron above, and you just pick up this very tiny row very nicely, and it's a library of imaging. And we did for alternative, very complex sample like assets, hearing. The electron microscopy often you can get, but almost cannot repeat this image because your electron microscope will just burn the sample finally to the end. But here it's a live cell, you can image quite lots of the pieces of some membrane, some collagen fibers, this very tiny microvilli, this is kind of high code. You see this very tall stereocilia picked up very nicely. And this was never done before, so now we can image the most complex sample and practically we can go to the tissue, brain slices, we have no limitation in the sample preparation because it doesn't matter how elaborate it will be, we will see the top projection. And we try different cells, for example, this kind of microbeta. And this is interesting, this is how we always compare. In London, we have a tower bridge, pillar, and then just connected with the road. That would be similar. This is a 10 nanometer in diameter protein link. And it's between two stereocilia. You can pick them up and image many times, never destroy them. And it's a fantastic, you can pick up the row, which is only 10 nanometer width, suspended in space, and you still can image it. And it's a fantastic, and it's a live specimen. So, it's a microwave. And you can go to the higher resolution. For example, sometimes in the collagen diagram, we look at the cell growing in the collagen. You can look at these very complex fibers, but then when you zoom on them, you can start to see all these 40 nanometer bands and the structure of collagen. So you can mix kind of generally very high depth of focus with a very, very high resolution at some point. And you can image bacteria, just I will just go like this human stem cells. So you see this tiny little projection, you can pick up all this structure very nicely. Actually, this is two frames of the same movie. You see the changes, you can follow the changes and dramatic alteration. And this, for example, cardiomyocytes, you can see this very nicely straight structure, the tejidos opening. So you can pick up perfectly any image. As again, neurons, you can see this very nice structure, you can zoom and just go and pick up. But because it's a live study, you can compare all with electron microscopy to 2D, very difficult to make a 3D out of it. But here we can do some exercises, like hyper stress, so you can see the same cells shrinking or swelling during the exercise. And because you can make a movie, and because it's not invasive, it's low resolution, because it was with patching but it's 24 hours moving, just leave it and go home, it continues the image, and you see how cells change in time. Or you see how this microwave move in time and much more rapid moving. So you can pick up lots of structure at the same time. And you can follow quite a number of processes, for example, how this microwave is developing, we'll just build a whole map, how we artificially painted them on that. So you see the green one retracting, the red one growing, so you can see how structure formed and how the cycle happened. And now lots of people from electron microscopy say, oh, we see the difference in our microwave, probably because they are dynamic, so we can just follow what's happening. And you can follow how this particular we study these kidney cells. You can form these breaches from microwave. They're very important for endocytosis or something. But you can see how these guys form in real time. So you see they just form and the reach. So you can follow this. You can follow different things because people study a lot, for example, of diffusion of protein. And it was quite interesting because you have to know what's happened in the cell. They often presume, oh, it's a flat sample, and we have this barrier for particle to move. But what kind of barrier here? You have to cross all these guys. Imagine if this is a tall structure. So if you want to move around, you can see how many obstacles you have. So it's completely changing the model how we look at diffusion of anything happen on the cell surface. And we study also nanoparticle uptake. It's a human lung cell, and you can see again, for example, this is a picture plotted in this kind of slow form, so it's like electron microscopy. And this is leading edge, you can see how changes happen. So you can follow lots of moving. But now, what I want to say that this just as a microscope, but often we see pictures through what? Not much. But the beauty of it, it's quite independent technique, and it's very easy to combine and build something more complicated. And this is where the interesting story starts, I think. So we can generate just a small fraction of what we did, but just first we tried to combine with optics. And here it was quite interesting. We just shoot the laser exactly where the tip. But instead of scanning the laser, we scan the sample. So practically it's like a sewing machine. You just have laser and you keep it at the same position, but the sample moves over that. You get topography, but also you precisely focus your objective at the surface of the membrane. So instead of making like a focal microscope will do slices, and then you have a problem. Where's the fluorophore was versus another sample, photo bleaching. And if you combine that, this is what you would get. But here, you get the picture in one go, topography and all your fluorescence distributed on the surface. And it's a fantastic way to follow something because you suddenly can do quantitative measurement. Because with confocal microscopy, you can't do any quantitative measurement. because you don't know relationship where's your fluorophore versus your focus. Here you always know, and with none decision. So we did lots of things like we can image the viral particle, we just look in the entry, and just taking up mapping them and trying to see how they aggregate, see where the virus is coming in, and we can link it nicely to all. But we actually explored this a little bit more and started looking at endocytosis. This is a cluttering paste, if you know the cluttering endocytosis. You can get transfected cells, so it's fantastic to optimize that. This will be cluttering. And you see the pits, very nicely cluttering pits opening, and then you just mark them opening like that, and you see where they link to the actual cluttering. GFP. And what we found, a very interesting phenomenon, it was quite aroused because everyone knows the model that cluttering just invaginate, they put the page code in. And actually, it's not happening like that. And what you would see that every time this strange phenomenon happened, like something happened here. And we started to measure electron microscopy, and we found tons of this evidence that something over the tape hanging out. And then when you look at the real movie, how it happened, the tape opened, we have to do fast. So the resolution is like we were losing because we have to do only 7 seconds per frame. But so we limit the number of pixels, but still you can pick up nicely pitch formation, and you always have this fluorescence. And you see finally the pit closes with this top. It looks like 2 pits, one, and then disappear, second one, disappear. So they always come with this very interesting lead. So we did quite a number of movies analyzing that, how it's happening. You can always see how it's happening. So it's very interesting. You can follow simultaneously this process. And as soon as the cluttering closes, it's disappeared. And you can follow this thing. So, yeah, we don't go on this model how it's actually happening, but just show you this kind of low resolution movie, but you will kind of see when you see many pits. So you see this slightly darker spots, okay? But before closing, you always see this just come. So another combination because the patch clamp impact, because I started this microscopy because I was doing patch clamp reporting, and to me it was so natural. Anyone who uses micropipette or nanopipette, that is a fantastic way to do that because it's practically like very advanced patch clamp. So what you can do, you can just get the optical picture, choose the big scan the area, for example, just land on the tip of the microwave and record some electrons from it with the same pipette, which you use for imaging. So it's the same tool. It's like a guided missile. Just pick up the target, just go there and pick it up. Everything by the computer. So it's very nice optimized. And you can record from quite difficult cells because sperm was very, very difficult to record, and you can easily do that. Or from a very, very fine dendrite, which is maybe only 100 nanometers thick, but you still can pick up very easily because your control over the distance is perfect, so you will never crunch your probe. It's always protected. And we started to study synapses because all this neuroscience, all the electrical signal, finally the synapse is a kind of holy grail. But actually we don't know much about them because we cannot report from them. If you report from the body, clone and know what's happening there. So this is a chance actually to study very small synapses separately. And with it now, you can image, you see this picture, you can focus on that, and because you can stain synapses, for example, to stain presynaptic vesicles, you can get this very complex network and graph synapse and those, pick it up. But what you can do, then you finally can go, just crack that and record some images. And just show you a couple of things how we do that. So you choose this optical imaging. This is how synapse is the highest resolution we could do, by optics to detect and do fluorescence. But because you get in topography with your thing, you see the photon very nicely attached to that, and you make this trace that you see in the border where this might happen. No, now you target that place, and it's automated almost position. You get a picture, pick on it, with a mouse, and you got a recording. And this paper I just got accepted to Neuron yesterday, so it's just the same. So that's quite nice. So this is what practically happened. You check this photon, you get that, and you record. But what's often important, just by optics you can't do that, because some butons could be underneath or inaccessible for patching, because we can't get to that. We see some dendrite, but button is hidden underneath. However, by optics you wouldn't be able to separate, but here you can do it very easily. And just example how button you can pick up, very nicely some ones which are very inaccessible, so you can see that very, very difficult to pick up from even tomography. Talking about optics. But what's important, you can record all these channels and characteristics, but it's not enough because we want to do a whole cell reporting. Because cell type reporting, you can't do pharmacology, and we want to do pharmacology. We developed a very simple way of chopping the D-pad, and it's very interesting. So the whole trick is very interesting. You use a sharp D-pad to get this beautiful picture, high resolution, but we want to pulse cell. So we can ask our program, just break the D-pad to a particular diameter. And what it does is chopping the D-pad, and very nicely ways you can see the size before and after. And actually you can get a perfect seal. And what more important, actually you can use the same D-pad to patch many times. By chopping, cleaning the tip, and go again and again. This is, for example, we've got a patch reporting and break the D-pad, and we've got another seal, we broke another seal, so you can continue till you're too big, to do anything. But the idea was to do a whole cell or whole button reporting. But that's by chopping the D-pad. We can now patch a button, and in this case we put a fluorescent dye into the D-pad, so we can load axon with all these buttons, nicely through the D-pad. It's very nice to validate that. And you see some capacity spike because you're reporting capacitance from button, neighboring axon. So you can report now lots of things from button, let's say sodium current, potassium current. We were studying calcium current. It's very interesting. We found something, because if you do cell patch reporting, we couldn't find a single calcium channel in the button. And we're patching from many places. None. As soon as you break the whole cell, you see lots of calcium current. You can block it. If you go this out configuration, so you strip a lot of the exposed part of the area, they don't calcium channel. So it looks like they all heated to this active zone. This is practically the direct evidence. And you also see that bigger button have a higher level of calcium current, it's smaller, so you can make a lot of link. But what was interesting, if you patch on the neighboring dendrite, you see this calcium channel easily exposed everywhere. So you can specially map channels even in such a tiny, small compartment. This is another combination. Now it's getting anywhere. So the probe you can combine with anything. This is very fancy work we just recently started to do, and you can a little bit excited. So the very related technologies where you can record some chemical species by oxidizing them or measure redox or potential on, let's say, platinum wire. And if you think it's like a nano-T-pad filled with, let's say, platinum wire, this is our T-pad like that. It's very, very similar. But what you can do, first attempt we did very complicated. We just got our T-pad. And the idea is because these chemical sensors, if you do a small one, you can't use it because you cannot control them over the sample. How to bring to the target? In no way. So we decided to use our feedback control by fine conductance so we can easily manipulate and map all cells again easily. So what we combine is put the T-pad, put platinum around, some insulated material cut on the iron beam. We've got the feedback control and set to measure them. It was fantastic. We were able to image, to see oxygen consumption by cardiac myocytes. We can get a relatively good picture. The topography was not affected. But then we moved to a slightly different way of doing it, and it's much, much more simple, and it's very versatile. We can use the double barrel T-pad and use a lighter, put a little bit from your butane to the T-pad, put another lighter, just hit it the tip, and suddenly you have a nanoprobe with a carbon tip, and the production takes you 2 minutes. You don't need to be a smoker, but you need a lighter. So you can produce nanotechnology suddenly, because what happened, the pull-up produced you this sharp T-pad, and that dictates what the size of the probe will be. So the previous probe cost 400 pounds for us to produce, and only 1 of 10 was working. Now this cost us in consumable maybe 10 pence. To produce it in 2 minutes, And that's it. So it's fantastic. And when people start to pick up, maybe it has some very interesting application. You can do lots of things and characterize it. When you started to break the pipette, you see this carbon is very strong, you know, just sticking out all this inside. And this is one barrel filled with carbon. You can analyze this spectrum, how much oxygen. And you can get very high resolution pictures. Again, we started to get the highest resolution picture they will ever get in with electrochemical microscopy. You could see with very high see how, let's say, sensory urine penetrates. This is more electrochemistry, I will just move on to this. But you can image neurons, you can look, for example, neurotransmitter release. So it's quite interesting because this is barrel. You can, for example, trigger with one pipette this potassium depolarization and see the release of neurotransmitter, or you can do the stimulation through the second barrel because you can fill this potassium locally apply and you see the spike because you locally trigger release. So you have suddenly this tool just in one pipette and very simple to use. You can do lots of imaging with that as well, just using the carbon probe. Just switch this here. But what's important is probes you can modify in such a way that we can make multi-barrel. This is what we just moved to that. We suddenly started to measure oxygen consumption, oxygen level very nicely by simply recording potential or measure this ROS species, which is very popular now in any kind of medical condition because reactive oxygen species is actually related to most of disease. You have a sunburn, you know, suddenly you have a problem or cancer, and that is because the UV increase this ROS production, and they may cause a cancer. And it's a big problem. You don't die because we have a heart attack, because your ROS species builds up straight away as soon as you have a hypoxia. But the case you can produce a multi-barrel pipette. One of them will measure carbon, for example, neurotransmitter, and another will measure your ROS species. So it's a very simple nanoprobe, which is easy to manufacture to measure. You can go and measure the ROS in the cell. So I move further. What you can also use the pipette for local application, and this is what we do with Antonia now in Nara. So the idea was because the cells communicate with each other. How we do experiment with them? We just put a chemical just into the dish. Forget about this. Cells never communicate like that. The whole signal is local. What you put from outside will kill the cell. When, for example, two neurons will send signal to each other and will be happy to communicate. But as soon as this level, for example, neurotransmitter increase, it will just kill everything. So you have to understand that lots of trigger, like ATP trigger, everything happens very local and it will be destroyed. And here we can mimic this with the pipette. Imagine you have a small sensor, it's almost like a synapse, you come trigger. But it's opening quite a lot of possibilities. Imagine you have a receptor. You come close to that receptor, you trigger. Let's say it's trigger calcium. You have this natural amplification, and you can monitor locally. If you apply here or there, and you can do an imaging tool, you actually can map function of receptors. There's potentially open quite a non-invasive way of recording by the, you can record functions. And I'll show you example how you can do that. But the idea was how to characterize what we're applying to the pipette, because it's very critical what happened at nanoscale. So we did lots of modeling how what would be this concentration, this dark red, with no pressure, for example, actually not much coming out. But if you apply pressure, you suddenly start to stream, for example, and how much you cover. So by doing that, you actually can use different sensors. What we did again, we used this electrochemical sensor, this carbon probe. So now we actually can apply something to the pipette and map this real measurement of the distribution of your agent which you apply. And you see the major concentration will happen rapidly drops somewhere like this. And the beauty of it, we try to apply to the trivial channel with what we do with Antonia. And that created something very interesting. Because if you add agonist to the neuron, it will be overloading this calcium. And that triggers tons of processes. It will inactivate many things. It's quite damaging, we know that. And you actually, if you want to test some drugs, you actually limit it because you cannot apply many times drugs. You have to go to the new cells and it takes forever. But here, because it's a very localized, you can apply even to the small part of the cell and get response and very quickly stop application. And this is the idea. Somehow skip some of the slide. Anyway, if I explain, what you see here, imagine this is a cell, this is transvected cell, this big channel. And the pipette will be programmed, can jump here, apply for 2 seconds, jump to another one, 2 seconds, 2 seconds, and apply a particular amount of stimuli. And by just measuring the slope, how quickly calcium gets in, because this channel open and the calcium just rushing in. And practically what you measure is called the response. So very nicely you can map everything, and very quickly, because something which took you a week, something you can do 100 times more in 1 minute. And that makes it quite important impact. So this is kind of example. You can just go with the pipette on neuron, and apply in several positions, and go and repeat again and again, and you see the reproducibility of this response. And you can do many times, and you can do a dose response. You apply less, more and more till you saturate. So you actually can very quickly get important data, and that could open quite a possibility. Imagine you want to test drug on human neurons. How many of them you can get? It's such a rare sample, and suddenly you can't do anything. Here you suddenly can perform hundreds of experiments without actually destroying them, and very rapidly. So it's potentially very powerful. Something else, just lots of physical measurement. You can measure surface charge density. It's quite interesting. It's actually, we don't have methods currently to do that. In this case, it's very simple. You just put slightly different concentration of salt into the pipette, and by coming to the surface, that will, if you have some charge, it will restrict one of the lines moving out, compose another. So immediately you will measure potential. So in this case, what we did, we just coated the dish like a print, some polylysine, which is positively charged, and glass is negatively charged. So if you just go to that, you can image the picture. You see a clear difference. This is negatively charged, this is positive. And when you approach, this is what you will see happening as a potential. So you actually can map something. And we did, for example, you apply to the cell with negatively charged particle. This is topography linked to that, and then you started to see the distribution of charges on the cell surface. And for example, very interesting, we look at the sperm. Maybe it's very much related to the physiology. This had just been after some reaction. This flagella goes. It's a principle piece. This part is full of mitochondria. It's engine, which drive the sperm. And now, if you look, this is polylysine and cell attached. The light X means more positively charged, and dark X is more negatively charged. So you see the hair somewhere has lots of negative charges, especially flagella. But if you know the ion channels there, the mostly cation channels will be localized here for calciumetry to swing, or in the head. But in the principal part, where you have mitochondria, you need a very nice, because this is where the oxygen and CO2 exchange happening. So you need lots of anion transfer. Now you actually make it very positively charged to enhance this transfer. So you see the cell is very nice care for the charge density. But again, you do nothing, you just change concentration in the pipette. Suddenly you see lots of information coming from your data. You see topography and suddenly the relatively charge distribution. I can't say exactly what the charge value from that, but I can say the difference. Another example, because we can deliver, and this is what we do in the training, but you can deliver different things through the pipette, and we just decided, okay, it's an inkjet printer. So eventually it's just going to put the DNA with attached part to it. So if you just apply voltage, it's just electrophoresis practically, you drive molecule because they charge to the tip, and you see each pulse send so many molecule DNA out. But if you put into the pipette, for example, this antibody, you can just write with them, and this is a fluorescent image, of course it's photometering quickly, but you see where you're drawing, you see what you're doing, so you actually can generate an image. But even more, you can print something. We were playing with different things, and this Cambridge, so we printed letter K, Cambridge crest, different antibody, and the student was playing this Newton phase. So okay, the glass was not treated well because they had to stick. Imagine this DNA, you printed the picture, okay, you can still recognize, but it's important, you can do in grayscale. Now, of course, we can make it a little bit more complicated. For fun, you just take double barcode pipette. In this case, you actually don't need any liquid. You can short the circuit like that, and you can do imaging in air. You don't need even liquid, because you wet it all. But also, you can print with it. And then the student put some battery into DARPA, into the computer, and then simply just bitmap file, just plug into software. And what it does is just simple different delay for what it's applying. But now you can print in color very easily. You have 3 pictures printed with that. And actually, but it tells you how well you can deliver something from the p-pad. And it's very easy. Because as soon as you control, you can bring the probe to the position. Now you can do some manipulation. Okay, this is fun, I don't know what for, but it's interesting you can do this on a cell. That is really important. Actually, we call it it's a nice security talk with your own DNA, your own photograph somewhere, and it's the smallest picture, you know. And you can apply just endless. You could imagine, you can put anything into the p-pad. You put acid, you can etch something, you can mill a hole, you know, you can do whatever. For example, mechanical stimulation. And that is something which very difficult to do. Atomic force microscopy does just put a stick, put it and push. But cells are hate it. And actually, you know, somebody who wears glasses know that they measure eyeball pressure. And currently you go to the microscope, somebody just put a puff of air. No. But originally it wasn't like that. People used real metal springs. And the physician was coming and putting against your eye and pushing. That was very painful and not very effective. Patients hated it, you know, you could imagine. But this is a very simple story. You can plug your p-pad, and you know, you touch, you rip it off, you know, and you can make a lot of damage. If you want to measure gamma sensitivity, it's rather injury study than gamma sensitivity. Here you can do simple things. It's like if you're watering anything, you know, you apply a jet, apply positive pressure, water flow, and if you bring it to the surface, it's pushing the membrane. But you never touch it, so you actually can follow, and you can measure quite a nice elasticity module, get all the physical characteristics, and it's very simple. You don't need this very complicated mass to convert how your interaction happens. Or you apply nothing, or you can apply negative pressure and apply the suction without touching the sample. And you can sometimes pull the tethers, like, you know, maybe microns. So it's a very interesting way of doing it. And we do now lots of measurement with that. It's very, very effective. Okay, this is also how it does. We did it on sensory neuron. You can look to get a picture and then position yourself. And we found something interesting. And this is what some textbooks are full of mistakes, because lots of things coming from electron microscopy. And you should imagine that is a sample which will fix. That means it's collapsed, and everything shrank. It's like starting the Egyptian movie and say, oh, this is a living human being, you know, this is different. And there are actually lots of mistakes. Like, you fix the sample, it's a fry net, collapsed, and you're actually losing a lot of information. So what I'm just saying that if you look at the neuron, in reality, when people draw lots of cytoskeleton attached to the membrane, it's not. It's actually, they are like a breathing place, because cells always have a metabolic state, you know, it changes volume a little bit, so it swell a little bit. And cytoskeleton is not following. This is a cage, you know, which holding, but the membrane can go quite off. And it's very important for function. I show you an example. You like the neurons, if you measure that, okay, if you pull the membrane, it's very easy because nothing holding it, you know. It's just moving away, and you need a very, very small pressure. But if you deform it, the first maybe 100, it's up to micron in sensory neuron body. It's almost no resistance. There is no cytoskeleton till you reach this cytoskeleton core, when you suddenly hit something and you start to measure mechanical kind of property of the cell. And it's important. So actually lots of things happen, and the exocytose and this region, which is actually not that heavily populated by cytoskeleton as everyone thinks. An example, for example, we studied aldosterone action, how it's controlled our blood pressure practically. We all know, you know, we need to control if you high pressure, you may have a heart attack, but it's also things responsible by our kidney. Kidney epithelial cells reabsorb sodium and control our pressure, and aldosterone helps that. So, and that is very important. If you look at these cells, how they look like a regular epithelial cell. And mechanically, if you again fix the cell, this is something that I wanted to show. We measure some mechanical characteristics, but as soon as fixation happens, we can do it live. The cell shrink immediately come off, like 2.5 microns, you see. And this very active zone become again collapsed, and you see that, and explain what next. So how does aldosterone works? Well, what we see that if we just get a cell monolith, resolution is low, I explain why, because it's actually on. When you stimulate, you see this stretching phenomenon in the first puzzle. You see like chessboard structure, the group of cells look like swollen. But in reality, if they are not swollen, they're contracted. What happened? The cell just like that, something contract, and it's like a toothpaste, because the epithelial cells are very symmetrical like that. We call them myocyte because they have this contractile belt. So they simply contract like a toothpaste. Could you imagine you push it, and the whole volume just pushed up. And this is what happening here. It just stay like that. When it's contracted, suddenly it just bulge. And what is interesting, if you just measure activity of this sodium channel, how it works, because the same feedback we can use to image and patch, and no activity. This cell is just full of ion channels, they just function. But if you look at what is actually happening with topography, as soon as it contracts, you see lots of microbeads. Suddenly, this membrane just like a glove stripped off. But we try to do electron microscopy. As soon as you fix at this point, it becomes this. So the membrane just straight away collapses back, and you don't see anything. But if you do electron microscopy, you just will not notice that anything like this happened because you cannot detect that. But what is interesting is channels. Nobody knows why, how they activate. What we know, they become sensitive. So if you break active filaments, they activate it. You add active. But maybe this is what we call the puzzle. If they hijack something from volume regulation. When this happens, the lots of linked to the actin filaments are lost, and maybe this will activate this certain channel. Because it's like a digital switch. There's no activity. As soon as it contracts, as soon as it collapses, you add a little bit of osmotic stress. It will shut down. With membrane, also collapses down. Very interesting. Then we found what is responsible is actually these cells use paracrine regulation. They release ATP, and ATP trigger this contraction. This replicate this will happen. And if you simply add hexakinase outside of the cell, actually your hormone is not functional anymore because paracrine signal comes into the cell, and then it's kind of variation mechanism. They secrete ATP, and that will trigger activation. But let me just a few examples how you can apply all this technology together. For particular, for example, cardiomyocytes. You can image this cardiomyocyte, see a particular structure. Get all this kind of architecture and everything. Then you can map this local application. For example, we were looking at potassium channel, ATP activated. So we just remove potassium completely, replace with cesium, but the pipette fills potassium. So when it's over the channel, it creates strong electrochemical gradients and it creates the current. So you can plump everything at zero, but when you go over the channel, you suddenly plus in there, you see this very nicely single channel, almost recording. So by that, you straight away can just during the scan map the position of the channel. So the microscope by itself doesn't see it. It just only applying, but another patch comes also recording, so we can detect. But this is now we can record single channel functioning. This is again, nothing else can do like that. And example, then you can patch, and this is something interesting with cardiomyocytes. If you know the structure of cardiomyocytes, if it is muscle, there is tissue, so it's a part of the membrane invaginate by dip inside. And most of the ion transport in the system is there. If you defibrillate the cell, there is almost no current. There's no ion transported system, except sodium current somewhere on the edges. So everything just removed. And what is beauty? Because it's about 200-300 nanometer opening. With our pipette, we actually can get even inside the tissue and patch there. And in this case, we recorded cell type calcium channel, which is sitting there. So it's quite interesting. And you can make a lot of map, the map potassium chloride channel, to even try to look at how the maybe repolarization or propagation happen of potential, because it's only a small step, 2.2 micron. But when sodium channel fire, but then cells alone, and if you actually measure membrane potential, it doesn't exist on the cardiomyocytes. Actually, you would have a very different potential in different compartment, because imagine each of this tissue, it's only 200 nanometer, very small compartment. Most of the ion transported, let's say potassium leak out, suddenly creates high concentration of potassium here are mainly very different there. So all this potential between two tubular regions become different. But it's propagate and try to equalize everything because nothing else can control because in our heart, because we have to synchronize everything. And this is how it's probably done. Another example again, mapping together this electrochemical, we could look at respiration, which is maybe very important, just general. It's all kind of using very similar technology, nothing special. Of course, topography could do a lot measure because we can see what happened after heart failure. For example, what we know now, they will be losing the tubular system. Practically, they're losing a lot of their functional system very quickly. And that must be what happened if you imagine imagine the cardiac myocytes and these T-tubules goes in. Imagine cells swell. What would happen? It's slightly started to increase, but these T-tubules hold the cytoskeleton, and they're like sausages, just break. And suddenly what you have, this enclosed compartment inside with all their transporting system. And that easily happened during the hypoxia, for example. The cardiac myocytes has enormous amount of, for example, ATP, 30 millimolar. Imagine all of it break suddenly too. You can double or triple concentration to the 90 phosphate and that will force cells to swell. So anything going wrong, they cannot turn it back to ATP quickly. You have this metabolic stress, and they straight away may be defibrillated, and so they cannot contract anymore. And this is what practically we managed to see what happened. Okay, you can measure mechanics very nicely. Cardiomyocytes is a very soft cell compared to the one on the surface. And you can find also very similar things. And you can compare what would happen with mechanics when it's kind of intact or immediately after heart attack, where we see very, very strong distribution. Part of cells become very hard, but another part getting much softer. So normal cell will have very good distribution. Here it become very wide. So often failure or cells kind of start to contract in a very open way, very kind of tricky elements. You can get lots of characteristics like that. You can do this mechanical stimulation, for example. You can stimulate here. If you push this movie, it's contracted, and you can see when. We're playing mechanical, and mostly when you're relaxing, that cancer trigger. So it's very interesting. It's not a mechanical deformation, and relaxation is bad. You can do this trick. You have lots of swimming pool. So if you just apply some pressure in the keypad and look at the cardiomyocytes when you're imaging, it's like I always drinking like that. Go drop into the swimming pool, it comes out, or the dress kind of very, very tightly. And you see all the details underneath. So it's exactly the same story. You just apply a little bit of jet. And while the imaging, suddenly you see this all fancy line, maybe some maintenance. So you almost see all the underlying structure. So actually you can pick up something what just believes the memory. It's simply blowing on the cell. And this is, for example, recently we did very interesting. Again, this local application, we see it's very powerful. We look what happened with beta receptor. And again, this is not direct measurement. What we use a threat. So for cytokine P. So if you get a normal cell, you have a beta 1 and beta 2 receptor. And it's very difficult. There's none of the antibody works. So nobody knew what the distribution of them. So you can come with a feedback and stimulate the cell and see the response in T-tubules or somewhere. So what we found, the beta 1 distributed everywhere, but beta 2 all hidden in T-tubular region. And this is what detubulation does. It's completely removed. But after heart attack, cells started to do something strange. They're all dead because they lost so many tubular channel system. They have to still function somehow. So they redistributed all the receptors all over the surface. So practically, that's it. I just wanted to show you that by using this very, very fine p-pad, you can actually do so many functions, and it's a very, very simple technique to actually do. Sorry, I didn't look at everyone. It's an update. And just last thing, we're developing, you're always welcome to try something if you have some idea.
So now, questions? But for sure you have many. Or you are so much surprised that
So if you want to perform an experiment with SICM, do you have any requirements in terms of pH in the media where the cells are?
The beauty is what it can't tolerate is only phthoric acid because it will dissolve pipette. And currently, for example, I've seen that lots of people study this for lithium battery study. For example, this is a very aggressive. Imagine it's very difficult to know what happened in lithium battery because you cannot know how this lithium was created, let's say, on this carbon electrode. Because if you expose to air or something, it will explode. So how you can monitor it? It's not easy to do electron microscopy, and what they know, the smaller crystal, the higher capacitance. They managed to do 10 micron. They said if you will make 1 micron, you will increase 10 times the capacity. Everyone now wants their phone running, for much longer. And now they started to use, because you actually can run in that organic liquid, because it uses iron, and use a lithium ion for image, and they just see what's happening in the battery when you build. So practically you can work in any environment. It just needs some conductive media, which have ions.
So in principle, could you apply neutralizing antibodies on top of a virus and see it? Because from what I've seen...
What you said exactly, this is what we're planning to do. One project we're running now on donkey virus. And it's exactly that problem with antibody, because they're known phenomena. It's very nasty virus, if you heard about it. Third world, killing more people than it's carried by mosquitoes. But the problem there is that antibody enhance infection about 700 times. So you add antibody and it becomes 700 times more effective. And this is a major issue. You fight against that and actually make it more effective. And they try to develop antibody which actually will do opposite. And it's quite tricky. So this is what we're trying to look now, how this binding this antibody with a viral particle affect their, let's say, entry at the moment. We don't become so much more. But it's true, you can, because some antibody are very big, like 30, like I show a picture of that protein. If you land antibody, which could be like 32 nanometer high, like normal antibody, you will see it just will be bigger than any other protein.
Any other question?
Do you need any kind of fixation of the sample? Not like trying
we actually
to avoid the movement of the...
You can. It's very easy to fix sample, but you may lose the beauty of having the one specimen. Of course, the movement is an issue, but this is what we love to watch, and we try to develop as fast as possible. Because fixation is a lot of art. People started to come to us because they try to find a way how to fix sample for electron microscopy. So far, nobody found the way. And we did quite a number of imaging. They tried, for example, use some detergent or something. So during the fixation, to make holes in the membrane, so it wouldn't collapse. But we did tons of images like that. You can't do that. Some cell will be destroyed by your detergent. When others will have no perforation and still shrunk, so it's very complicated. But you can use fixed sample easily. It's easy, much easier.
I was thinking just about if you want to measure on a liposome. Usually I try to do it and then it moves, and then we have to put in a support like mica, for example, to do AFM.
No, fixation, for example, we try to do linkers. It's very difficult. They're running away. We look at the blood vessel. We just run. Of course, sometimes you need something to you just float. You can't do that. You have to attach it somewhere, another side to some position.
The limits of the scanning speed.
So this is the problem for any scanning probe microscopy. We try to move now, like in joint force microscopy, people started to move to this so-called high-speed system. And we're making some progress on that, and it's quite possible. We try to do now in collaboration with Andy in Japan, because he moved now towards high conductance, because they still suffer
but the scanning tool is slow. What we could do, hopefully, we can go to video rate, but with restricted number of pixels. Currently, we reach about 7 seconds per frame, but we easily can move that, but we need just to make better pieces. Right. We limited one pieces at the moment.
Any other curiosity? No? Okay. Thank you very much, Yuri. Thank you very much.